Hi, welcome along to a little video deriving PV equals a third PV equals a third Nmcrms squared. Not the assumptions leading to its derivation, which have been examined much more frequently. You'll have to look those up separately. Pressure pascals or newtons per metre squared, volume meters cubed, number of particles, mass of an individual particle, and CRMS representing root mean squared, a way of showing the average of the speed of the particles, which we know is distributed over a range. A little bit of background, you all know Pythagoras, but it works equally well in 3 dimensions. So if we can imagine moving along an amount x, kind of back into the page an amount y, and then moving up an amount z, this resultant, and if you think about it, that's because we make another right angle triangle, that's root x squared plus y squared in a right angle triangle with z, and anyway, it works, and we're going to need that later. The first part of the derivation revolves around thinking about the momentum changes of a particle in a box, and that's just fine. And probably the bit that's most likely to be examined, I haven't seen it examined for about 20 years, but when it was examined, the bit absolutely that they examined was the bit about the initial momentum change. The latter part is rather more statistical, and I think it would be quite hard to set questions on, and it's not really covering anything else that you've done. I can't guarantee that that's not what they'd ask, and also I've seen it done so many different ways. So you might see it in other places with the cube or the cuboid that's being imagined. They've interpreted it as having a different dimension on each face. I'm going to assume that it's a perfect cube, and therefore all the dimensions are the same. We're interested in a particle. It will have mass m, some velocity c, and we're just interested in the component of its velocity in the x direction. And what we're going to do is we're going to imagine it colliding with this face, and we want to know the pressure it exerts on that face. Obviously, the pressure will be the same on all faces. So it's coming along with momentum in that direction, mvx. It will have an perfectly elastic collision, go back the other way with momentum mvx. So delta mv, the change of momentum during that process, is 2mvx. To calculate the force it exerts on average over a period of time, not the instantaneous force in this case, either case we'd be using this equation. So we need to know the time between successive collisions. Speed is equal to distance divided by time. So time is equal to distance divided by speed. In this case, and this is one of the things you've got to kind of watch for, the distance between collisions is 2L. So it's going to start here, travel L, hit there, we're not interested in that, come back to here, and it will have travelled a distance, 2L at a speed Vx. So the mean force averaged over time is the change in momentum, 2mvx, divided by the time, which is 2L over Vx. Dividing by a fraction, we just multiply by the reciprocal. So the force is equal to 2mvx multiplied by Vx over 2L. Okay? And then that will equal, the 2's obviously cancel, you get mvx squared. So that's the mean force with time exerted by one particle on that face. The pressure is equal to the force divided by the area, isn't it? So the force is mvx squared, and the area of this face is L squared, isn't it? So it's times by 1 over L squared. And we get M Vx squared over L cubed. And this is looking somewhat hopeful in terms of our derivation, because we're just about to start seeing some of the things that we would recognise from the end of it. Because clearly L cubed is equal to the volume of that container, isn't it? The volume of that cube. So we've now got P is equal to mVx squared over the volume, or for a single particle on one face, PV is equal to mVx all squared. So now the next bit on the next page, I'm going to generalise that out to consider the effect of many particles. But I think the bits on this page are the most likely bits for somebody to ask questions about. So I'll just write what we've already got here. We've got PV equals mVx squared. Now, if we want to generalise this out to n particles, we're going to need an RMS value of this, the mean value of this, not just the value of one. And then we're just going to say, so the pressure due to n particles, so I haven't changed what I'm writing here because this is the pressure for one, this is the pressure for many, is n mVx RMS squared. Now, on average, for a randomly moving particle, it will be moving randomly equally in all three directions, okay? So CRMS squared by Pythagoras will be equal to, and this is where I think this is a bit of a, because you could argue that I could have done the Pythagoras first on the, not the means, and I have seen it done both ways, so I think that's one of the reasons I think it's a harder bit to examine. But on average, these three things are equal, aren't they? So that's just equal to 3 times the x value, and mean x value of the velocity squared. So finally, and you can see now where one of the bits of the final outcome is coming from, is a third CRMS squared. So going back to here, we're going to replace Vx RMS squared by a third of CRMS squared, and we get PV is equal to n m CRMS squared. And there we have it. That's our final result. Thank you very much.